Yesterday we studied classical mechanics in the context of symplectic geometry, and we were able to generalize a great number of objects in classical mechanics to the symplectic geometry setting. Today we're going to reap the rewards of that hard work, and we're going to introduce and discuss integrable systems, which is a concept that we can now make completely precise in the new setting. But before we do so, we have some prerequisite material to cover on Young-Jin submanifolds. And in order to talk about what these Lagrangian submanifolds might be, we have to first talk about what is a submanifold. So we'll spend a couple of minutes making that concept precise before we get onto Lagrangian submanifolds and then integrable systems. So if you have two manifolds, M and X, then, and if X has a lower dimension than M, then it's reasonable to ask the question, is X or can X be identified with some subset of M in such a way that X is a manifold in its own right, which inherits the manifold structure from M? It's one way of posing the question. And the answer is sort of surprisingly difficult, and we have to introduce a lot of adjectives before we can make sense of X as a submanifold of M. And the first step we need to take is to understand in what sense is X a subset of M. We're going to have to identify the points of X in M and then increasingly add adjectives until X lies in a nice way inside M. And then when we've had enough adjectives, we'll be able to define the word submanifold. So the first step towards identifying X as what should be a submanifold is we've got to identify points in X and M. So for that we need a map. So there's our map, I. And the first adjective we need is that this map is an immersion. So this is like a necessary criteria, but not a sufficient criteria for X to be a submanifold of M. And what does immersion mean? Well, it means if you take dip at every point, that's some map from the tangent space at the point P of X to the tangent space of the point IP of M. So the bare minimum we'd want from a map that identifies X inside M is that this map is at least injective. One to one. I mean, if that wasn't, then you'd be really in for problems. Now it turns out that's not enough for the map I to identify X as a submanifold of M. Lots of things can go wrong if your map is just an immersion. So we need another adjective. In particular, if you look at this condition here, you see that it's a local condition. Doesn't say anything outside of an infinitesimal neighborhood of a point P. So you can imagine that things can go sort of wrong on slightly less local scales. So we can fix that up by using some information about the topology and introduce another adjective, embedding. And embedding is an immersion, which is a homeomorphism onto its image. now they have the same structure as topological spaces, so X and the image of X in M. But things can still go wrong. So I'll give you a little example. So some mapping of the open interval 0 to 1 into R2. And I'll decorate the ends with arrows. So this is an example of an immersion which is not an embedding. So we need more adjectives, it turns out. Because there can be nasty embeddings, so you wouldn't want to call every embedding a submanifold for nasty, because there's some nasty things that can also go wrong. So we come up with the notion of a closed embedding. Another adjective. It's an injective, immersion, such that the preimage of any compact set is compact. And there's another word for that. That's called proper. If the preimage of any compact set is compact, then you call it a proper map. And this is the final notion that we're going to use to talk about submanifolds. So let's give an example of something which is an embedding but not a closed embedding. What is such a thing? Such a thing doesn't have this weird property at endpoints, for example, but it has the property that a compact set gets pulled back, or the preimage of any some compact sets are not compact. So let's try and cook up one of those. And we've actually seen this example before. The way it works is the manifold R gets mapped as a submanifold of R2, not a submanifold, sorry. So R gets mapped into R2, the torus. So this is what this means here. And how does it get mapped there? Well, we take the point X in R to X alpha X, where alpha is a rational. So then that's something that looks like this. Etc., right? This is a nasty example. You can see if you have a compact set in here which is closed and bounded by the Heine-Borel theorem, then it gets pulled back, its pre-image is some infinite union of closed sets, which is not closed and bounded. So that's an example of an embedding but not a closed embedding. And as a little exercise, so as the name suggests, a closed embedding is an embedding. Well, it's not quite clear from the definition. So it's an exercise, and the image of X is closed in M. So the image of this map here is definitely not closed in M. And that's it. Now we have enough adjectives. We can talk about what is a submanifold now. So a submanifold is a manifold, X, with a closed embedding. There we go. Yep, a question?
Regarding the exercise, how could we show that every embedding is a closed embedding? That is not true as we've seen.
So the exercise, the question is, how can we show this? The exercise is, if you have a closed embedding, then that means that it's an embedding and the image is closed. And the other direction is, if you have an embedding such that the image is closed in M, that's a closed embedding. I mean, the words suggest it, but the definition doesn't make that manifest.
Yeah, because I saw the equivalence symbol.
Oh, yeah, that's if and only if, yeah. So there's two statements on the right-hand side of the if and only if. So a map is a closed embedding
with the image. Okay,
with the and.
Okay.
Yeah.
Thanks.
That was all. So we're going to think of this embedding map I as just a straight up inclusion, so that the points of X are just the point identified with their points in M. And the tangent space is just identified with its image as well. And then we'll just forget about this map I when we talk about submanifolds. Okay, now we have submanifolds, and we can talk about things called Lagrangian submanifolds. It's very useful for our discussion of integrable systems. So a Lagrangian submanifold, as the name suggests, is a submanifold. And because this is a course on symplectic geometry, it's going to be a submanifold of a symplectic manifold. So there it is. There's our symplectic manifold, M omega. And it's 2n dimensional. It's even dimensional, right? All symplectic manifolds are even dimensional. And the word Lagrangian is taken to echo the definitions of subspaces of symplectic vector spaces. So a Lagrangian subspace of a symplectic vector space is a set of vectors whose such that when you restrict the symplectic form to them, you always get 0. So that's what a Lagrangian submanifold will attempt to generalize. So at every point, P and Y, the tangent space is symplectic vector space, right? That's what a symplectic manifold has, the property. It's locally a symplectic vector space. So we have that everywhere the tangent space to Y is a Lagrangian subspace of the tangent space Tp of M. Which means that if you restrict the symplectic form to Tp of Y, you get nothing. And furthermore, that just means it's isotropic. To make it Lagrangian, we need that it's the highest dimension possible. Equivalently, as if you have some inclusion of Y in M, then it's Lagrangian if and only if the pullback of the symplectic form is just nothing, and the dimension result. So a good example of a Lagrangian submanifold, we met it yesterday in classical mechanics. It's just the submanifold given by all the generalized, all the canonical coordinates of the classical mechanics phase space. And if you have a cotangent bundle with a standard symplectic structure, as we saw, then also we get a Lagrangian submanifold given by just the manifold M itself. Now we have enough information to build and explore a notion of integrable systems. So integrable systems generalize our favorite systems in physics, namely the harmonic oscillator, to a vast array of different examples. And using the theorem we met yesterday, we can even understand a little bit the structure. Okay, let's formalize something we observed yesterday in studying classical mechanics as an example of a symplectic manifold. We generalized that study yesterday to a definition. So we're now comfortable that the infrastructure we've built around symplectic geometry is capturing the essential aspects of classical mechanics and therefore can legitimately be seen as a generalization. And to crystallize that generalization into a definition, we introduce the notion of a Hamiltonian system. So what is it? Well, it's a symplectic manifold plus a Hamilton function. Now, there's many examples of Hamiltonian systems. Remember, any symplectic manifold, any smooth function on it will give you a Hamiltonian system. But some are more special than others, right? Like the harmonic oscillator is definitely special as a Hamiltonian system. It's special because you can, well, for very many reasons, it's got lots of symmetry in phase space. Its trajectories are circles. Maybe that makes it special. Or it's special because we can integrate it, right? There are other one-dimensional systems where you can't write down the integrals, the first integrals, so easily or at all. Maybe that's what makes it special. Well, we're going to extract one feature of the harmonic oscillator today that makes it special, namely that it's integrable, and we'll give a definition for that. And to do that, we're going to first prove a theorem about the Poisson bracket. This, if you like, is the generalization of the conservation of energy result from a couple of lectures ago. And so the beauty of our definitions is that this is, again, a three-line proof, like yesterday, for other properties. So firstly, we let sigma t be the flow generated by a vector field x of h. And then we're just going to look at how does the function f composed with the flow change with time. So the function f is a zero form. That's important to keep in mind because we're going to be able to rewrite this using the pullback and the Lie derivative. And then the Lie derivative of a function, we exploit this other formula we have for the Lie derivative, dix plus ixd. To write the Lie derivative like that. And then we can find the corresponding vector field for f via the symplectic 2 form. But that's the Poisson bracket in disguise. And so we're done. So we have this criteria for functions that remain constant on the flow, namely functions that can symmetric under the flow. And the criteria is that the Poisson bracket with h has to vanish. So we have a name for such things, straightforwardly generalizing the terminology in classical mechanics. So such a function is called an integral of the motion. Or constant of the motion. Or first integral. So these are all synonymous. Now there's this intuitive argument, right? If you have enough constants of the motion and they're all independent, then you should be able to solve your system. If you think to quantum mechanics, we have an analogous statement there. If you have enough operators that commute with each other, then you can simultaneously diagonalize everything. So we're going to, if you like, inspired by the quantum statement and the quantization map I talked about yesterday, we can discuss what might be meant by a complete set of commuting observables in the classical setting. And if you ponder that theorem up there for a little bit and try not to think of H as having a distinguished role here, H is just a function on the manifold, F is just a function in the manifold, then we can cook up a definition for what might mean a complete set of commuting observables in the classical world. So if you have a collection of functions, f1 through to fn, and we don't want that they're the same function. Like, the stupidest thing you could do is choose f2 to be 1 times f1 and f3 to be 2 times f1 and f4 to be 3 times f1. So those functions, we want to find a set of independent functions, functions that behave differently as you on the manifold. And if we have enough independent functions, then we ought to have enough first integrals to be able to fully integrate our system of equations. So what is the notion of independence? Well, we're going to call them independent on a symplectic manifold M if if df1 at P, df and P are linearly independent. For all points P. So that's the notion of independence that we're going to use in discussing first integrals. Ah yeah, independent for all P in some dense subset. Right, they might not be independent for all points in M, but as long as they're independent in some dense subset of M, then that's good enough to call these functions linearly independent. So suppose we've got a bunch of independent functions. Now, let's think about the quantum setting again. You've got a complete set of commuting observables. You can simultaneously diagonalize everything. Now, we learned yesterday that the commutator of quantum mechanics should be identified with the Poisson bracket in symplectic geometry. So the natural notion of complete set of commuting observables in the classical setting ought to then be a set of functions, as many as you can take, which have pairwise vanishing Poisson bracket. That should be the analogous notion. And we're going to call it completely integrable We're going to call a Hamiltonian system completely integrable if you can find as many independent functions as possible which are integrals of the motion. And we're going to name them F1 through to Fn. And the first one we'll take to be the Hamilton function itself. And it's not enough that they all commute with the Hamilton function. We furthermore want them to commute with each other. And if we are in this happy circumstance, then we call the Hamiltonian system there completely integrable. And of course, these things are special, these systems. We can say a tremendous amount about the structure of the manifolds when you have a completely integrable Hamilton system. Just as in quantum mechanics, you can say a tremendous amount when you have a complete set of commuting observables. Okay, let's just note something obvious, right? So if J are such commuting integrals of motion, then at each point, the vector fields coming from these integrals of motion generate a Lagrangian submanifold, or Lagrangian subspace, to be a bit more careful. The submanifold bit comes later. At the moment, we can definitely say that we have a Lagrangian subspace generated by these XFIs, FJs. And that's because we know that XFJ, XFK equals 0. So we also learned something else just from symplectic vector space theory. If these are independent, these FJs, then there can be no more than n being half the dimension of the manifold of them. Okay, let's find some examples of integrable systems. And I've already said one example, right? I already motivated this example. I motivated our definitions with this example. However, A couple of other examples that are worth mentioning. So the simple harmonic oscillator, well, yes, it's completely integrable. And so is the simple pendulum. Actually, that's pretty cheap, right? Because it's completely integrable if there exists n equals to half the dimension of the manifold first integrals. But when the phase space is two-dimensional, half of 2 is 1, so you only need one first integral for the system to be completely integrable, and we have such a first integral. It's called the Hamiltonian, so we're done. A much more interesting example, and to illustrate sort of the exact criteria you need to fulfill to have an integrable system, happens in 4 dimensions. So if you have a 4-dimensional space of symplectic manifold, then to be completely integrable we need 2 first integrals, not one, that are independent. And you have one first integral, that's the Hamiltonian, so all we need is one other independent first integral, and then we know the system is completely integrable. And there's a really fantastic example which you should cover in the coming assignment sheet. I believe we'll set this as the next problem on the assignments, namely that of the spherical pendulum. I believe we'll set that to be the next assignment. Right. So now we're going to take a look at what's the analog of a level of an integral curve when you have more than one integral of the motion. So every integral of the motion, you could in turn interpret it as the Hamiltonian and the other functions as integrals of the motion, thanks to the definition. The definition is completely symmetric for a completely integrable system. And so it makes sense to talk about not just the integral curves of the Hamiltonian, but like the integral surface generated by these independent vector fields. So let's suppose we have one of these special integrable systems. We have a lot of independent integrals, first integrals. Make it 2n dimensional. And we have our list of first integrals. There's n of them. First one's the Hamiltonian. And we're going to study the preimage of these functions here in our symplectic manifold M. Value. So you take these functions, there's n of them, you form a vector of these n functions, and that's a number. This is always an element in Rn. So you can think of this as a map from M to Rn. And we take a regular value for this, so not a critical point. So there's a level set given by the preimage of that point in M. And what can we say about this level set? Well, in dimension grounds, we know that it has half the dimension of M. We can look at the differentials, and we can look at the vectors, the vector fields tangent to this level set here, and we see that all those vectors pairwise commute, so we know that if we restrict to the subspace of this, if we restrict to the subspace of tangent space of M, then the symplectic 2 form restricted to the tangent space of this level surface vanishes. So this should be a Lagrangian submanifold. Indeed it is. We can say actually a lot more about this particular Lagrangian submanifold. It's not just any old Lagrangian submanifold of M. In fact, it has some very special structure. So let's suppose that either our symplectic manifold is compact or that these vector fields are complete, so we can integrate them for all time on the level set f minus 1 of C. So this lemma here shows us that the level sets aren't just crazy Lagrangian submanifolds of the symplectic manifold, but in fact they have a very special structure. So if you think to the harmonic oscillator, what are the level sets? They're just the trajectories, which are closed curves. They're circles, right? And that's a perfect example of a torus. And so in the case of the simple harmonic oscillator, indeed it's the case that the level sets f minus 1 of c at regular points are toruses, so k equals n in that case, which is 1. There are other completely integrable systems, like the simplest one possible is a particle moving at a constant velocity with no potential. There the integral curves are straight lines. There that's an example where the level sets are just r. And this lemma, although it's written as a lemma, tells us that this is basically all there is to know. So as you study completely integrable systems, the level sets are really just products of things you've already seen before, namely straight lines and circles. And the proof, I'm not going to include the proof in this course, but you can reconstruct the proof using the exponential map and the Poisson subalgebra. So we met Poisson algebras yesterday and the corresponding Lie algebras, and the fact that this Poisson algebra generated by these commuting functions, well, it's a commuting Poisson subalgebra. So the exponential map can't really give you anything other than circles or lines. So completely integrable systems are very special. Now, in this course, we will no way get near the theory of more general theory of dynamical systems and chaos, but there is this notion of integrability sort of carries over even to chaotic systems. So you can have systems which are chaotic. That means the level sets don't look like this at all, right? They're all folded and mashed up inside the symplectic manifold. But there are little islands of integrability. This is good. And why do we call them integrable islands? Well, because they locally look like little toruses inside the larger phase space. So although the trajectories of the system are going crazy all over the place, there are still little islands, little tori living inside locally near points in phase space. That's called the CAM theorem. Kolmogorov, Arnold, Moser. So there's a very interesting corollary of this. Just adds an adjective and we get a much stronger consequence. Any compact component of the level sets well, the word compact's there, the real line's not compact. So it must be a torus. I'm going to give this torus a name, it's the Liouville torus. Okay, and we're going to end the lecture today with a theorem, very lengthy to state theorem, which packs this all together and derives even more powerful consequences. first of the power theorems of symplectic geometry. Well, apart from the Darboux theorem. So we can say a lot about completely integrable systems, and now we're going to. So we start as before with a Hamiltonian system, m omega h, and we want it to be integrable. And then we'll immediately learn stuff about the level sets of the system already from the lemmas that we've proven. We're going to learn a lot more. Okay. So we start with a completely integrable system. There's the data of a completely integrable system there. Symplectic manifold, a Hamilton function, and n-1 other first integrals that commute, pairwise commute with the Hamiltonian. And then let, as before, C be a regular value of the map F, vector valued map F. Then we know that the level set is a Lagrangian submanifold. And now let's summarize further consequences of this statement, of this information. So if the flows so you take your integrals and you flow them, you form vector fields F1 through to Fn. If you start from some point which is in the level set, starting with those vector fields, and you flow via the exponential map, and if they're complete, so they don't sort of terminate in finite time, so we know, thanks to the lemma, that this connected component is of this form here, containing the point P. And we know a bit more. We can introduce a coordinate system on this component. And these are called the angle coordinates. So in proving the lemma that I wrote above, sort of one of the side effects of that proof is that you can introduce this coordinate system where all of these flows are linear. And that's just because the Poisson subalgebra generated by these integrals, first integrals, is a commutative Poisson subalgebra, and you have this Lie algebra anti-homomorphism that we discussed yesterday onto the vector fields. That's pretty neat. And if you think to the harmonic oscillator, the coordinate along the level sets are circles. So there is a natural coordinate on the circle, namely the angle. And the flow is linear with respect to the angle, right? The angle increases at constant rate as time passes on the harmonic oscillator. And this shows that that's not just specific to the harmonic oscillator, but is a general feature of any completely integrable motion. But there's more to this theorem. This is like the easy half, A. We've already basically proved it, although I omitted the proof. But here's the hard part, which definitely won't prove in this course. So there are coordinates psi 1 to n, conjugate to these angle coordinates, called action coordinates. So this should start to ring bells from classical mechanics. You should remember action angle variables. And these coordinates are integrals of the motion. And these angle coordinates, together with these action coordinates, form a Darboux coordinate patch. Or a Darboux chart. Again, this is omitted for this course, especially part B, which is very challenging. B is rather interesting. So this Darboux chart implies that the Poisson brackets between phi j and psi k are in fact delta jk's. So they're really conjugate variables in the sense of classical mechanics. However, and here's the something you have to be a bit wary of. You might be tempted to think that these action coordinates are just the values of the integrals of motion. It's very tempting to think that. It's certainly true in the harmonic oscillator case, where basically nothing else it can be. And the reason is actually pretty simple, right? Because these things don't form a Darboux chart. just take a look at some examples. I've already mentioned them very many times. Example 1 is the harmonic oscillator. So there's the integral curves. Here's a point C. Well, C equals F inverse of C, to be more precise. F1 equals H. There's only one bad point, that's at the origin. So these level sets are just circles, and you have indeed an angle variable phi 1, and you have a conjugate coordinate going in that direction there, psi 1. So psi 1 is the radius, and phi 1 is the angle. Note already at the level of a harmonic oscillator, this is half r squared, that the action angle variables, or angle action variables, are not the same as the first integral. And then we'll have another example, so this one's much more complicated. So the simple pendulum. So phase space for the simple pendulum some pretty characteristic picture that you should have seen, I hope, at some point. Okay, I assume you've seen the simple pendulum's phase space before. Now, this phase space has some very interesting features. So depending on the momentum of the system, the solutions of the simple pendulum have two vastly different behaviors, right? So for small energy, when the system has a small amount of energy, the system oscillates like so. And that's what you see here in this phase space in the center here. So the trajectories are as you would expect from the harmonic oscillator. But with enough momentum, or enough energy, the system no longer executes simple harmonic motion, or nearly simple harmonic motion around the origin, but in fact swings freely over and over and over again. And that corresponds to these trajectories here, these unbound trajectories. And right in the middle, you have these asymptotic trajectory here, which is where the pendulum starts at the top, at asymptotic infinity, swings around, executes one oscillation, and ends up pointing upwards again at t is plus infinity. So those three types of trajectories are all here in the phase space of the simple pendulum. And now you can see the complexity of level set. This is an integrable system. It's completely integrable. In terms of elliptic functions, Cn and Sn. So you can look up these, the equations for the trajectory in your favorite elliptic integrals textbook. This form isn't particularly useful, however, knowing the solution. is actually not really particularly useful for understanding the system as a whole. So it's a completely integrable system because the phase space is two-dimensional. We have that for free. And let's look at the level sets and compare them to what we know about the level sets from the Arnold-Liouville theorem. So we've got three places, three different behaviors. Let's try and understand the level sets there. So if we pick a point here, then that's on a level set, and the level set's an ellipse. Coming from the Cn Sn type solution of the elliptic of the pendulum. So anywhere here, if your trajectory is inside this separatrix area here, the solution is just an ellipse, and we have action angle variables in that region here. Phi 1 is the angle, which you have to distort a bit because it's on an ellipse now rather than a circle, and you have action variables. So you have a coordinate chart which works in this region here to decompose the level sets into tori. It's just straight toruses here. And then there comes this critical region here which separates level sets from being tori and level sets being the real line. Because if you pick a point outside the separatrix here, then every trajectory out here is of the form of the real line, right? It's no longer a torus, it's actually open. And so we see that even within such a simple system here, even within the smallest phase space available, we can exhibit the features of this Arnold-Liouville theorem, namely that the level sets are tori or real lines or products thereof. Or we can't get products thereof in the case of two dimensions, but you can see that even within one single integrable system, your level sets can actually change behavior depending on where you are in the symplectic manifold. And so what the Arnold-Liouville theorem says is that this isn't just some freak of this particular example, but in fact all completely integrable systems exhibit level sets like this, possibly separated by separatrices coming from critical points. All right, I think I'll stop there. And yes, next week we'll start getting onto moment maps. Thank you very much.